join us there. So today, the talk today is about the Rust borrow checker and how to use its guidance to write safer and more powerful code. So enjoy the talk, which will be short and sweet today, but I'm sure it's packed of very useful information for you guys. So enjoy the talk, and we will be back with Nell at the end of the talk for the Q&A.
Hello, everyone around the world. Thank you so much for having me here today. When I work with someone who is just learning Rust, they sometimes question whether the Rust borrow checker is their friend or their foe. If you take a look at the Rust subreddit, it's common to see posts with headlines like this: newbie question regarding the borrow checker, help fighting the borrow checker, and does it ever get easier fighting with the borrow checker? However, as you watch people get more experience in Rust, they tend to come around to the borrow checker and realize what it protects them from doing. So in answer to the question, is the borrow checker a friend or a foe? I say, the borrow checker will become your friend through experience. And along with gaining experience with it, it's also very helpful to understand how it works and why it does the things it does. We're going to dive deep into that, but before we do, let's briefly cover who I am. I'm Nell Shamrell-Harrington. I'm a principal software engineer at Microsoft. I was formerly at Mozilla on the Rust team. I am also one of the directors on the board of the Rust Foundation. I am also the lead editor of This Week in Rust. If you're not subscribed, I hope you do. It'll help you keep up to date with all the fantastic things the Rust community is doing. And if you want to get in touch with me, Twitter honestly is the best way, so just tweet at me at @NellShamrell. And to set expectations, we will first do a bit of background on the Rust compiler in order to put the borrow checker in context. Then we will do a deep dive on the borrow checker. And let's go ahead and start with an overview of the Rust compiler. And let's take a look at a code example. This Rust function declares a vector composed of the integers 1, 2, 3, 4, and 5. And after it declares this vector, it then uses a for loop to iterate through each integer in the vector and print it out on a new line. If we were to run this with cargo run, let's go ahead and run it. As expected, we would see the numbers 1 through 5 printed out on the screen. This seems pretty simple. Cargo builds and runs this piece of code for us. But there is a lot that happens underneath the surface in the compiler when Cargo is building it. There are 5 general stages to compiling a piece of code. It starts with lexical analysis of the code, then parsing of the code, followed by semantic analysis. This is where the borrow checker comes in, optimization of the code, and finally code generation, where the compiler creates the executable binary of our code. When we look at the stages laid out in a list like this, it might seem like they will run linearly. And in some compilers, they do. However, if you've delved at all into the Rust compiler internals, you might be thinking, wait a minute, isn't the Rust compiler at least partially query-based rather than linear-based? And the answer to this question is yes, but that is out of the scope of this particular talk. For the sake of clarity, I'll speak to the internals of the compiler as if they were functioning linearly. However, if you want to delve more into how the Rust compiler is query-based and what that means, check out the guide to Rust C development for more information. This guide has been a big help to me as I've learned how to hack on the Rust compiler. Going back to the stages of compilation, let's start with this first one here, lexical analysis. During lexical analysis, a program within the compiler called a lexer takes the raw Rust source code, called a lexeme, and analyzes it, and then splits the code into tokens to make it easier for the compiler to parse. And that brings us to the next stage of compilation, called parsing. In this stage, a program within the compiler called a parser analyzes the tokens generated by the lexer, and then translates them into an abstract syntax tree, or AST. Having the tokens in this data structure makes it much quicker and easier for the compiler to do the rest of its work. And at this stage, before it moves on to the next stage of compilation, the Rust compiler in particular takes the abstract syntax tree generated by the parser and first expands any macros included in the code. If we look back at our code example, let's zoom in on this line. Printline is a macro, which means this line would be expanded to this. This is what the full printline macro looks like and how it would be represented in the abstract syntax tree. At this point, the compiler also desugars some of the syntactic sugar that makes writing Rust so delightful. For example, in Rust, the for loop is a piece of syntactic sugar for an iterator. If we were to desugar this section of code, it would consist of both a match statement and a loop. The functionality of this code is identical, but desugaring it makes it easier for the compiler to understand it and to optimize it. At this time, the compiler will also resolve any imports in the code. So if you were bringing in an external crate or using internal crates or modules, those would be resolved at this point as well. After these steps, the compiler then takes that abstract syntax tree and lowers it or converts it into the higher level intermediate representation, or HIR. Let's pause here and take a closer look at the data structures that make up the HIR, so it helps to understand them. The first structure is a node. This is identified by a here ID, or HIR ID, and that node belongs to a definition. A definition is an item in the crate we are compiling. These are primarily top-level items within the crate. This is identified by a def ID, and a definition is owned by a crate. This is the crate we are compiling with Rust. It stores the contents of the crate we are compiling and also contains a number of maps and other things that help organize the content for easier access throughout the compilation process. This crate is identified with a crate num. This is the original Rust source code we are compiling. And let's focus on this section here, the for loop that iterates through the numbers vector. Remember, this for loop desugars into a match statement and a loop. If we look at the node in the HIR that represents this match statement, we would see something similar to this. It's a little hard to read for humans, so let's go ahead and break this down. This arm struct represents a single arm of the match statement that our for loop desugared into. And in that arm, first we have the here ID for this piece of code. This identifies a node within the HIR, or higher level intermediate representation, and that node is owned by a definition. The definition is some top level item in the crate. And that definition data structure is owned by a crate data structure. So our for loop is a node within a definition within our crate. And that's how we can identify where this node corresponds to our original code. What also helps us do that is what is called a span. This stores the file path, line numbers, and column numbers of the original source code. This will be very important in the future as we optimize and desugar the code further. If we were to encounter a problem with the code after it is desugared and optimized, we still want to be able to show the user where in our original source code that the error was generated. If we were to show them the desugared code, which is different from the code they wrote, it wouldn't mean that much to them. They need to know what part of the code that they wrote caused the error. The compiler then takes the HIR and lowers it again into the mid-level intermediate representation, also known as the MIR. The MIR is constructed as a control graph. The units within this graph are called basic blocks, which are identified with values like BB0 and BB1. Within these blocks, each has a sequence of statements that execute in order. The very last statement is known as a terminator. This controls when and how the program proceeds to another basic block. This is pretty simple. This is a pretty simple example. There's only one direction the basic blocks can go. But if our code had an if-else statement, then the terminator of BB0 would have the option to either proceed to BB1 or to BB2. In this case, there is more than one path that the program can take when it encounters the terminator in BB0. There are definitely more data structures involved in the MIR. If you're curious, definitely check out the guide to Rust-C development. Again, it's a fantastic resource. I cannot recommend it enough. Let's go back to our desugared code. And let's zoom in on this match statement, which is assigned to a variable called result. If we looked at the MIR, the mid-level intermediate representation for this piece of code, it would look similar to this. And I have simplified this for the sake of appearing on a slide. Up here in the top left, we have our basic block identified as BB2. And then we have what is called a local. A local in the MIR represents a place in memory, or more specifically, a place on the stack frame. In this case, _5 corresponds to the value of the variable result. And like in the nodes in the HIR, we have a span, the piece of the original Rust source code that each node in the MIR corresponds to. Again, if we encounter an error when we're operating within the MIR, we can still easily refer the user to what lines in the original source code were the source of the error. And that brings us to the third stage, and this is big in the Rust compiler, semantic analysis. This is where the compiler tries to figure out what the programmer is trying to do in a way the compiler can understand, and then it translates it into machine code. And at this point, after it's lowered the HIR into the MIR, the compiler will run several checks, including the borrow checker. And we'll come back and dive deep into the borrow checker in just a few moments. But for now, let's focus on these last two stages of compilation, optimization and code generation. These stages are where the code is transformed into an executable binary. And the Rust compiler will use LLVM to do this for us. LLVM is a commonly used collection of modular and reusable compiler and toolchain technologies. The Rust compiler uses it to further optimize the code and generate the machine code to run it. Before it uses LLVM, the Rust compiler takes the MIR we created earlier and lowers it into the LLVM intermediate representation, or LLVM-IR. And the LLVM-IR is pretty unreadable to humans, but it looks something like this. And as you can see, it's still organized into basic blocks, like the MIR. We then use LLVM and pass it the LLVM-IR, and then it runs more optimizations on it and emits machine code. It then links the machine code files together to produce the final binary. And that's why when we call cargo run, we see these numbers printed out. So yay, that gives you a bit of an idea of how the compiler works to take your Rust source code and make it something a computer can execute. At this point, I do want to go back and take a deeper look at the borrow checker. In order to do that, let's use a different piece of code this time. If you're reading this code, looking at it, and thinking this will error out, you are right. We'll see how and why that happens in just a moment. First, let's go through this code line by line. We declare the variable x and give it the type of string. And then we set the value of x to the string hi RustLab. Then we say that the variable y's value is equal to the value of x, and then we attempt to print both variables. When we try to build this piece of code with cargo build, we get an error, and this error is a result of the borrow checker. Let's go through how the borrow checker identified this error. The borrow checker does several things, including tracking initializations and moves. How this plays out in our code is when we start with this first line where we declare the variable x with a type of string, x is not actually initialized yet. It won't be considered initialized until it is assigned a value. If we look at the MIR for this line of code, we see that x is represented by the local _1, and local underscore 1 is assigned the type of string. Now let's look at this line of code where we create and assign the hi RustLab string. Now that x has a value, it is considered initialized at this point. We create a new place in memory, local underscore 2, where we store the hi RustLab string. Then we move the value stored at underscore 2 to underscore 1. Remember, underscore 1 corresponds to the x variable. So we have created the string in memory and moved it to be the value of x. Now let's look at this line, where we attempt to create the variable y and assign it the value of x. This line is where the value of x is moved to y. And if we look at the MIR created for this line of code, we see that y is assigned to the local underscore 3. Remember, a local represents a place in memory in the MIR. And underscore 3 is given the type string. And then the value at underscore 1, remember that represents x, is moved to the value of underscore 3, which represents y. This means when we get to here, where we try to print x, x is not initialized at this line, so we cannot print it. And that's what generates this particular error. We're attempting to use a value of a variable after it has been moved. Something I'd like to specifically call out is how the compiler shows where the error was generated from in the original source code. It uses that span we talked about earlier. Even though we had lowered this code to the MIR, or mid-level intermediate representation, we still tracked what items in the MIR corresponded to what places in the original Rust code. This is very helpful to the end user. What is also helpful is this. The Rust compiler not only tells you what the error is and where it is, it gives you a command to get even more information about the error so you can fix it. If we run this command, we see not only an explanation of the error, but also a piece of example code that would generate it. Then the message gives you even more information about how to fix it. This suggests using a reference to borrow a value rather than attempting to move the value, which we saw done in the MIR representation of our code. Let's run this code using cargo run, and once the compiler builds the code and executes it, we see the message hi RustLab printed out twice. Rather than fighting the borrow checker, we used it to make our code even better. And along with tracking initializations and moves, the borrow checker also deals with lifetime inference. Let's go over what this means. Rust uses the word lifetime in two distinct ways. The first is to refer to the lifetime of a value. That's the span of time before the value gets freed. Another word for referring to the lifetime of a value is referring to the variable scope. Let's see how this plays out in our code. And let's start with this first line where we assign the value of x to this string, or we assign the value of x as this string. At this point, x is live, its lifetime begins here. However, when we get to here and we went back to the original code where we moved the value of x into y, this is the end of x's lifetime. And then when we get down here and try to use it again, x is dead. Its lifetime is no longer in effect, which is why this program will error. The other way Rust uses the term lifetime is to refer to the lifetime of a reference to a value. This is the span of code in which the reference can be used. Let's look at our corrected code, where we assigned the value of y to be a reference to the value of x. If we look at the MIR for this line of code, we remember that the local underscore 1 refers to x, and the local underscore 3 refers to y. And we see that the underscore 3 local is assigned a reference to the value of underscore 1, rather than moving the value into underscore 3. Looking back at our code, let's experiment and let's alter this slightly. And let's try to drop the value of the variable x before we try to print out the value of y. When we do this, and attempt to build this code using cargo build, we get an error. We can't drop X at that point because it is borrowed, and that borrow is used again later. The borrow checker tells us that X, because it is referenced by Y, needs to stay alive for at least as long as Y needs to stay alive. X's lifetime must be greater than or equal to Y's. Looking at this in the code, again, this is X's lifetime. And this is what needs to be the lifetime of Y, which is a reference to X. Notice that even though they overlap, X's lifetime ends before Y's lifetime is supposed to end. Y can no longer reference the value of X after this line, and at this point, Y along with X would be dead. In order for this code to compile, the lifetime of X must last at least as long as the lifetime of Y. The overarching way the scope and the lifetime of a reference relate to each other is that if you make a reference to a value, the lifetime of that reference cannot outlive the scope of the value. As I move toward concluding this presentation, I want to make sure you know there is so much more to the Rust compiler and the borrow checker. Again, please check out that guide to Rust C development if you want to know more. It's a fantastic resource. Going back to this question for the beginning, is the borrow checker a friend or a foe? I say it's a friend, though a very strict one. But the best thing about this friend is it will not only tell you when something is wrong, it will also tell you how to fix it. And I find that to be one of the best qualities I can find in a friend, as well as one of the best qualities I can find in a compiler. Thank you.
Thank you, Nell, for a very lively talk on an extremely technical subject. I'm sure that everybody enjoyed your highly pedagogical style and the liveliness of your presentation. So now we are ready for the Q&A. And let's see if we have questions from our audience, if they have anything more they want to know.
I'm glad people are enjoying This Week in Rust. I noticed that in the chatter during the chat. That makes the work really, really worth it.
There you go. I'm sure. I mean, it's very popular. It's a subject that really people enjoy. Okay, so first question: how do I get started contributing to the compiler?
Right. So I think the best thing to do is the compiler team meets in Zulip. There's links to their Zulip channel, I believe, on the Rust language website. If you're not able to find them, just ping me on Twitter or something, and I'm happy to connect you to it. And what I did was I went to them and I said, I'd like to get started contributing to the compiler. I'm completely overwhelmed, though, with all the different aspects of it. I've contributed to the compiler, and I still feel overwhelmed by a lot of the aspects of the compiler. So I asked, what are some good issues I could get started on that someone might be willing to mentor me on? And they pointed me toward a few of them, which really, really helped. I learned early on that no, you don't need to compile the entire compiler every time you make a change, because that was taking 40 to 50 minutes for each change on my laptop. There's little tricks. Some of them are in the Rust C development guide, which I linked to. And then others, it helps to have someone pair with you, at least through your the first parts of your contribution, to learn little things about what it's useful to do and what it's not to. So I'd say definitely reach out to the compiler team. They're very, very friendly.
Okay, that's good to know. That the community is friendly and welcomes new contributors. Another question: what do you think about the current attempt to leverage GCC to compile Rust code?
I think it's awesome. I have limited experience with GCC, but I've liked it when I've used it. I think if it allows faster compiler times, that's something with the Rust community surveys we hear every year is people love Rust, but the compile times take a long time. So if it can enable faster compile times sometimes or all the time for people, I heartily support it. And I think the more people who understand how the compiler works and how it can be changed, the better.
All right. Do we have any other questions? Let's see. Do you believe the example of the Rust borrow checker will inspire other existing languages, maybe even dynamically typed or interpreted ones?
I do believe it will. And I think, I came to Rust from a Ruby background, which is a dynamically typed language. And it was hard initially to get my head around the borrow checker and why it does what it does. But after I learned Rust, I started learning C++, and then I understood, oh, this is what it's preventing me from doing. And I really would have opened up security holes if I had actually done that, and Rust prevented me from doing it. So I do think that feeling of safety is one of the things people love about Rust so much. So yeah, I'd love to see it inspire other existing languages, even dynamically typed interpreted ones. It'd be very interesting to see a dynamically typed language that doesn't need a garbage collector, which is one of the things you don't have to have with Rust.
Great. So another question. Oh, suggestions. People want suggestions on books not Rust related to learn about compilers.
Yes, I definitely have a suggestion on this one. So I took computer science courses in college, but computer science was not my major. And one of the main ways I learned how compilers work was through reading a book called The Imposter's Handbook. I believe it's available online. I don't think it's available through Amazon or anything like that. But if you search for The Imposter's Handbook and put programming or something like that, you'll find it. It has a wonderful, very plain English walkthrough of the different stages of compilation. I referenced it into my slide, or referenced it in my slide that was listing out the different stages of compilation. It really helped me understand how compilers work.
Maybe we will look for it and we'll put a link in the chat.
That'd be great.
For this book. Okay. When you move a value in Rust, is it like making a shallow copy in C++?
So this was something I learned after I learned Rust. I started learning C++, and quick joke. Whenever I make a shallow copy in C++, I want to sing the song "Shallow" from A Star Is Born, because this is what happens when theater kids learn programming. But it is different. In C++, when you make a shallow copy, you make a copy of what's in the stack, but you don't make a copy of the value that corresponds to what's in the stack in the heap. You create another item in the stack that points to the same item in the heap. What Rust does is, yes, it creates a new variable that points to that same value in the heap, but it invalidates the first value. That's the difference. That's what the borrow checker forces you to do, and that means you're never going to have a situation where you're referring to memory that is no longer valid because you deleted the first variable. So it's a little different, but conceptually it helps to understand it.
Okay. Are there resources you would recommend or repos with examples for more complex scenarios to better understand borrowing and related issues?
That is a good question. For more complex ones, I don't have any off the top of my head, though I have no doubt that they exist. And if they don't, that sounds like a great topic for a next talk, or a topic for someone else to do a talk on, or I'll write up a blog post on it. So please do, and I would love to feature it in This Week in Rust.
All right. So someone should accept this challenge. What do you think about, okay, I don't know how to read this.
I don't either, actually. I think it's Miri. I think that's how it's pronounced.
Yeah. Okay. What do you think?
I've seen it in print many times, but I've never actually said it out loud until now.
Yeah, exactly. What are the advantages of using it?
Miri is not something I'm super familiar with. It's only something I've only heard about. But again, that's another great topic for someone to write up a blog post or something on, and something I personally would love to learn more about.
All right. So this is another topic to be investigated. Do you know of any automatic bulk conversion of alien code to Rust, such as C or C++ or Java?
I saw that someone in the chat recommended c2rust.com. That's the only one that I know of that's similar off the top of my head. So thank you, the person who put that in the chat.
Thank you from everybody. Is this the book that you were talking about?
It is, absolutely.
All right, great, fantastic. So this is so at least we have a complete reference to it for everybody.
Absolutely.
Yes.
I mean, that's what you're avoiding in Rust versus what you might have happen with making a shallow copy in C++. The danger is a dangling pointer where it's trying to point to memory in the heap that is no longer there.
Okay, so this is a clarification on the previous question on the analogy with the C++. Looks like that passing by value, when the caller doesn't require it anymore, is the way to write idiomatic ref code. Anyway, is passing by reference performing better?
That's a good question. I'd say it depends on the scenario. That is another one I actually don't know off the top of my head whether there's a performance gain by passing the reference rather than passing the value itself. Something I'm interested in learning more about.
Right. So maybe another challenge for for another talk or some blog post. All right. Here is someone wrote a novel. Okay, so I worked through the book. I'm new. I watched a whole bunch of Ryan Levick's and John Glazer's content.
Their stuff is fantastic.
Yeah.
So another high recommendation for learning more about Rust and getting more into depth with Rust.
So we can read that he's interested in API and the WSM. Definitely struggling with the with the string module system. Okay. So, all right. So this is a love declaration for Rust.
I'm so glad to hear that. Yeah, particularly the loving the language, loving the community. I'm glad that you love this week in Rust. So the best thing about the Rust community is I say we are a community where personal maturity and empathy are as important as technical excellence. That's very different from a lot of open source projects out there. I came to Rust because I wanted to learn a systems programming languages to work on a distributed systems project. I stayed because I was so welcomed by the community. So I was glad that you love it. I'm glad to hear that.
Okay, maybe we have a last question. Yes. What are your thoughts on Linux kernel and Rust?
I think it's fantastic. Your language has really made it, I think, when it's included in a kernel. I'm glad that it's that Linux kernel developers have this interest in including it, and it shows that even stuff that's historically been written in C, C++, Rust is seen as a viable language for extensions. I don't see them rewriting the entire Linux kernel in Rust. Just like Microsoft is very interested in Rust, is writing a lot of things in Rust. I don't see them rewriting the entirety of Windows, which is hundreds of millions of lines of code in Rust. But it shows that people are seeing the value of writing new things in Rust, or translating certain components where it makes sense to translate it from C, C++, and Rust. So yeah, I'm delighted at the prospect of Rust being included in the Linux kernel.
Beautiful. So it looks like we have another question, maybe. Any thoughts on Rust and Zig collaboration?
I don't actually know what Zig is. So no, but I'm curious now. Yeah.
All right. So somebody will have to write something or give a talk on this.
Absolutely. Yep. I'm not the only one who can talk about Rust. We need, particularly with This Week in Rust, even if you feel like you're learning a concept and you feel like it's basic what you learned about it, still write it up, please, and submit it as an article This Week in Rust. We have people of all different Rust levels reading it. I learn something from it every single week through editing or being the lead editor on it. Please write it up and submit it to This Week in Rust. Oh, it's a new language. Okay, cool. Please, someone write that up.
Wonderful. Okay, so for any other questions that you might have and you didn't get a chance to ask, you can join our Discord channel where Nell can answer the other questions that we have the link above. And other than that, you can see the recording of this video in our YouTube channel. And we thank you very much for participating to today's talk. We thank Nell for a very interesting and entertaining talk.
You're very welcome.
And we will see you at the next conference.
All right. Take care, everyone.
Bye-bye.